Hey guys, welcome to the Energy Notes. For those of you joining us, we have a new addition to the video notes. We're going to offer you chances to earn extra credit, and just so you know, it'll be 20 points on your last notebook check, and I think a few of you could use that. So here's how you're going to earn that. As you're going along filling in your guided notes, you are going to write a saying at the top of your paper, and I'm going to tell you the words to that saying. The catch is, I'm not going to tell you when I'm going to tell you those words. Trust me, I'll make it clear, but what we want to avoid is you guys skipping through the PowerPoints and only finding out what the secret message is. So, here's the first word to that saying. Energy. So right now, go ahead and write energy at the top. Right, that's the beginning of your saying, and by the end of the slideshow, you're going to have a saying, and you're going to email that to your teacher, and that's going to result in 20 points extra credit on your test. Or excuse me, your notebook. So, energy. Here we go. What is energy is something we're really going to learn to discuss tonight, and we're going to talk about it even more in class and have a lot of videos and applications for you. In order to understand energy, first off, by definition, it's the capacity to do work and cause motion. In other words, any push or pull that's going to cause something to move, that's energy. Anything you're putting in to cause an object to move, that's energy. Most importantly about energy is kind of the thing our kids get confused the most, is what unit is used to measure energy. And if we take a look at it right here, our unit is in joules. Okay? Now, you can know that 1 joule equals 1 kilogram times meters per second squared, but don't worry about that at all. It's not important. Just know that if I'm measuring something in energy, it's measured in joules. In other words, the more joules equals the more energy. Now, we're going to have different types of energy as we go along, okay? Now, potential energy is one of those types. Potential energy is stored energy. It has the ability or potential, hence potential energy, to move. And there are two types of potential energy. There's elastic. Okay, so you can think of things like the slingshot down here. You can think about a rubber band. You can think about a slinky. Anything that it can be stretched, and then when we let go of that, something is going to move. So in other words, potential energy causes movement, but it's not actually movement itself. So potential energy can be broken down into elastic potential energy, and also here we can look at gravitational potential energy. Energy by an object's position. In other words, the higher an object is, okay, the more potential energy it has. Now, the cool thing about gravitational potential energy is you're going to be able to calculate it, which you probably don't think is that cool at all, but we're going to do it. And it is mass times gravity times height, or MGH. So we've got a sample problem right down here for you. Okay, it says a 65 kilogram rock climber ascends a cliff. What's the climber's gravitational potential energy at 0.35 meters above the base of the cliff? So what I want you to do right now is pause it and go ahead and try to figure that one out. Now that you've figured it out, let's see what the answer is. And if I pull it away, you see that you use, MGH, 65 kilograms times 9.8 meters per second squared, 35 meters, and you come out to 22,295 joules. If you didn't get that, make sure you put a star by it, and we'll go over it in class tomorrow. Moving on. Now, in contrast to potential energy, we have kinetic energy. Now, keep in mind, though, that kinetic energy is still a type of mechanical energy. It's just a different type. So the two types of mechanical energy we have are potential energy and now kinetic energy. And if you'll notice in all of these pictures here, something is moving, whether it be the cannonball, the cheetah, or the bowling ball. Kinetic energy is the energy of motion. So the amount of energy depends on, once again, mass and velocity. So you can calculate kinetic energy, and here's the formula for it. 1/2 mv squared. So you can also write that mv squared over 2. It's the same thing as 1/2 mv, or 1/2 times m times v squared. But keep in mind, it's still energy, so the unit is joules. So let's practice that real quick. So here's your formula, 1/2 mv squared. Here's your practice problem. Go ahead and pause it now and try to figure that one out. Alright, now that you've paused it, we're coming back. It says, what is the kinetic energy of a 44 kilogram cheetah running at 31 meters per second? Super easy. 1/2 times 44 kilograms times 31 meters per second squared comes out to 21,142 joules. Keep that in mind. That joules is very, very important there, guys. And moving on. So just like the many laws we've seen the law of conservation of matter, we've seen the law of conservation of mass, we've seen the law of conservation of momentum. We've got another law of conservation here. Terrible line, sorry. But this time it's the law of conservation of energy. And just like all the other laws of conservation, it says that energy can never be created, can't create it, and we can't destroy it, but we can change or transform it. This is incredibly important for you to understand because we're going to go through this concept a lot in class. In other words, the net energy is the total amount of energy in a system, and the total or net energy must stay the same. So we can't lose it, we can't destroy it, but we can, by all means, transfer it. So, taking a quick pause here. Remember how we said you can earn extra credit. The first word in your statement was energy. The next word in your statement, you can add this up at the top. The next word is. That's your word, is. So now we have energy is. So energy changes on a roller coaster. We can talk about if we're at the top of our roller coaster, we have a ton of gravitational potential energy, GPE. Now, as we move down the roller coaster, all of a sudden our height begins to decrease, so our gravitational potential energy decreases. But we don't lose energy, right? What ends up happening is all of a sudden as we begin to move, we gain kinetic energy, so this begins to increase. And when we get down here, what we've done is we've taken all of our gravitational potential energy and converted it completely to kinetic energy, or energy due to movement. Vice versa happens as we begin to go up the hill. We take that kinetic energy and think about it. What happens here, guys? We start converting it back to gravitational potential energy. So at the top of this hill, we've taken all this kinetic energy here and converted it to gravitational potential energy here. Now, it's not a perfect system, because if you think about it, roller coaster tracks we have air resistance, we have friction, we have all kinds of things that are actually other energy transformations. So, are we saying that all of our gravitational potential energy has been converted perfectly to kinetic energy? No. Some is lost in the transformation to other types of energy, but we still have a pretty good transformation. So it's exactly what I was talking about. And you can read this, pause it and read it, or move on. Let's talk about more energy here. So I've already talked about mechanical energy, energy stored in an object due to motion or position. All right, we presented that already. So the two types of mechanical energy are potential here and kinetic here. They are both mechanical energy. And an object can have both mechanical and potential energy at the same time. Completely plausible. You can think right here about this paper airplane. If it's moving, it has kinetic energy. And also, if it's in the air, it's going to have some sort of gravitational potential energy. We have chemical energy. Now, this is where we're really going to go back to that chemistry we talked about early in the year. And we talked about those electrons, and we said those electrons form ionic or covalent bonds and sometimes metallic bonds. Well, no matter what type of bond it is forming, the bond is where energy is stored. So energy stored in the bonds is the most important part of this slide right here. You can look at all of these pictures. All of these represent some sort of chemical energy, whether it be food, batteries, gas, or the process of photosynthesis, which we'll talk much more in depth about when we get into class. So that's all chemical energy, energy in bonds. We've got electrical energy. You guys use this and see this every single day. We'll have an entire almost mini unit devoted to a day of electrical energy. Talk about when you plug in something, where's that actually coming from? We've got nuclear energy. Now, those of you who are really smart will figure out very quickly where nuclear comes from. The nucleus. Okay, so this is energy that we have released or harnessed from the nucleus of atoms. And we're using this in South Carolina currently. In fact, some of the energy running your computers and your light bulbs at your home right now are coming from small nuclear explosions, believe it or not. We've got thermal energy, hence the name. It's energy from heat. So we can look over here. We've got thermal energy in a fire. In a fire, we also see radiant energy or light energy. Energy associated with what we call the electromagnetic spectrum. We have an entire unit to that one. So fire is giving off all this light. It's giving off all this heat. In other words, it's giving off all of this energy. And we also have sound energy, energy associated with the movement of sound waves. Believe it or not, once again, another unit in our book. And we'll talk about what a sound wave actually is. Does it require a medium or not to travel through? But those are the basic 7 types of energy. Quick recap. Chemical potential energy, nuclear potential energy, mechanical potential energy, electrical potential energy. Alright, so we can have multiple forms of the types of energy. And we'll talk a lot more about that in class tomorrow. Energy conversions. These are where you guys really need to begin to get really good. And this shows us that you can actually take what we've taught you and begin to think about it in a kind of a more meaningful way. So I have an example over here. I say, what type of energy conversion occurs in a light bulb? Well, just think, where does that light bulb begin as far as the energy? And clearly it's electrical energy, right? So we have electricity in, and then we have heat and light come out. And that makes sense because you need to put electricity into a light bulb and you get that heat and you get that light being emitted. It's pretty basic, right? Well, what I want you to do right now is I want you to pause it. And I mean it. Pause it. And I want you to go through and see if you can come up with these energy conversions down here. So pause it now and try to. Now that you've paused it, let's come back and go over them. So a fan. Well, we're going to assume that the fan either runs off, let's say it's a fan that runs off, or you have to plug it in. So clearly, you're going to have to use electrical energy. And what do you get with a fan? You get kinetic energy. Energy due to movement, right? Those fan blades whirling all around. Definitely kinetic energy. A battery. Well, as I'm sure many of you know, a battery has chemicals in it. So we start with chemical energy, and we end with, think about what batteries do for you. They power electrical devices, so we end with electrical energy. Now a fire is a weird one, okay? So a fire, how did you start the fire? Who knows, right? We could say it starts with chemical because we have those chemical bonds in the fire, and then it ends with a multiple different kinds of things. We can say heat, or we could say light, but those would be kind of our best answers there. So we're breaking down the chemical bonds here in the wood, and we're resulting in heat and light being produced for us. And then a glow stick, the ever popular glow stick. Well, if you think about glow sticks, what do? You crack them, and then when you crack them, you're mixing the chemicals. So we start with chemicals, and then we end with light production. So all of those are energy transformations. We're not necessarily losing energy in those situations, or we're not creating or destroying energy. We're just transforming it. And keep in mind, it's not a perfect transformation every time. We do have loss of energy, which is what brings us to our last slide. And before we begin this last slide, let me tell you the final word to your statement that you're going to email to your teachers. And the final word is awesome. So I'm sure you have those 3 written down. What you'll do is you'll take that statement and you will email it to your teacher, and like I said earlier, it'll result in 20 points extra credit on your last notebook check grade. And what I want you to do before you come to class tomorrow is think about this example. It says, as a swing moves back and forth, the energy is converting from one form to another. I think we can agree there, right? Why will the swing eventually stop? In other words, it's not going to swing all day long. And in what form will the energy be transferred into? So think about these transformations from here to here, and why won't it always keep going back and forth? Alright guys, don't forget to email your teachers if you want extra credit, and make sure your guided notes are filled in.